Hello and welcome. I love learning about the technical aspects of game development. So, 18 months ago, I set out to learn about two specific topics: Tri-planar tessellated terrain shaders and running burst compiled jobs on parallel threads. A natural use case that combined these two topics was creating large terrains that could be manipulated smoothly in real time, without tanking the frame rate. In this video, we consider this terrain manipulation, or terraforming, and the data-oriented design and memory management required to make it run smoothly on parallel threads. Since the reasons for choosing to do things in a certain way in each step is motivated by the requirements of one or more steps following it, let's start at the final step and work our way backwards, motivating our choices as we trace our steps back to the beginning. Like the other 3D objects in our world, the terrain itself consists of a mesh with vertices in 3D space and triangles connecting sets of 3 vertices. Here you can see a wireframe version of a terrain. The final step, after all the calculations required to terraform the terrain have been performed, is applying the updates to the terrain mesh. While we can attempt to run the preparation steps on parallel threads, this final step of applying everything to the terrain mesh happens on the main thread, since the graphics APIs are single-threaded for safety and stability reasons. But there are some things we can do to improve performance. Firstly, the more complex the mesh, the more data needs to be sent around, the slower the update step. So if we can reduce the complexity of the mesh, we can speed everything up. However, this brings with it some downsides. The first downside is that a less complex mesh has fewer triangles and becomes more blocky or low poly. Luckily, there is something we can do about this. Remember that I also looked into tessellation for the terrain shader. We can send a lower detail mesh to the GPU and the shader can fill in more detail using tessellation, as long as we also send that detail through to the GPU. But wait a minute, we've just reduced the complexity of the mesh because we didn't want to send so much detail to the GPU. How does it help us if we have to send that detail through anyway for the tessellation? The secret to the performance gains we can achieve lies in the fact that we can use much less memory to get the relevant detail to the GPU, if we rely on some predetermined structure in our data. Let's see how and why. Each vertex of the terrain mesh contains an X, Y, and Z coordinate, placing it in 3D space. Each of these coordinates is a float that takes up 4 bytes of memory, for a total of 12 bytes per vertex. However, only the elevation or Y coordinate is really variable or dynamic. By design, our X and Z coordinates form a square grid of points, a fixed distance from each other, and these never change. Making the grid finer adds more detail, but also requires more memory and calculations, so there is a trade-off. But once the grid resolution is set, the grid points remain fixed on the XZ plane. If we know the location of the origin, which we can simply choose to be 0, and we know the distance between grid points, we can actually calculate the X and Z coordinates for each grid point. Furthermore, if we index the grid points from left to right, bottom to top, and we know how many grid points there are on the X-axis, we need only a grid points index to determine its XZ coordinates. Alternatively, if we have the XZ coordinates, we can calculate its index. But why would we go through all of this trouble? Well, let's get back to the elevation or Y coordinate. In our data structures, we can now ignore the X and Z coordinates and have a native array on the CPU side and texture on the GPU side for only the Y coordinates, packed into memory in the same order as we have indexed the grid points. This means we use only a third of the memory, or 4 bytes instead of 12 per element. But I went even further. We don't actually need the accuracy of 4 entire bytes. If we use only 2 bytes or 16 bits, we are able to store integer values from 0 to 65,535, or 2 to the power 16 values. If we split our elevation range from the bottom of the seafloor to the top of the tallest possible mountain up into 65,535 discrete steps, we can pick the step closest to the actual elevation as a very accurate estimate. One reason why the developers of games like Timberborn and Whiskerwood use such discrete steps in their terrains is because it requires very little memory to store elevations if there are only a few possible values. So even with discrete steps in elevation that are visually indistinguishable from continuous values, we now use only 2 bytes for every grid point instead of the 12 of the mesh. And that's without considering the mesh entries for triangles and normals, which make the mesh data even larger. Now, anytime that we work with a vertex of the mesh, we know its grid point index, so we can calculate its x and z coordinates and also know which element in the native array and texture corresponds to it. So we can both set and sample its y coordinate. But wait a minute, we've already sent all of these to the GPU as the mesh vertices. Why send it over again, even in a shiny, more performant way? This is where the tessellation and the extra detail it requires come into play. Let's keep the density of our mesh grid the same as before, but subdivide each cell into a 5x5 grid of its own. So we now have 25 times as many grid points as before, each with its own elevation. We send this extra detail through to the tessellation shader as part of a texture that also contains other data used by various shaders. For example, slopes. Here you can see how the shader fills in tessellated triangles in different ways depending on parameter choices. Using all the information we've discussed up to now, the shader can determine the grid point closest to it and get its elevation for each vertex it adds. It can even perform bilinear interpolation between the 4 closest points if you really want to, but that doesn't really add much visually. This process allows it to add detail in between the lower resolution grid points of the actual mesh. Now, every time we want to change the elevation of any of these higher resolution grid points, we make sure that we adjust both the native array of elevations as well as the packed texture that is sent to the GPU. Additionally, we have a native array of vertices for the mesh, which we only update if the changed grid point also lies on the lower resolution grid, which is every 5th grid point on both the x and z axes in our example. Sending the altered texture to the GPU is fast enough to allow us to do this every frame, even for large terrains, for a very smooth terraforming experience. However, refreshing the mesh isn't quite fast enough, even if we perform all the preparations in burst-compiled parallel jobs and just copy the already up-to-date vertices and pre-calculated normals to the mesh to update it. The update step is simply too time-consuming. We can counter this in 2 different ways. Firstly, we could update the mesh only every, say, 15 frames, as you can see in this scene. Secondly, we can suspend the mesh update until the current continuous terraforming action completes when the player releases the mouse button, and only then update the mesh. You may be wondering why we need to update the mesh at all if the x and z coordinates remain fixed and the shader simply uses the more detailed elevation data to determine the y coordinate. There are 3 good reasons for updating the mesh. Firstly, the player's interaction with the terrain takes place through the mesh collider, which will not be accurate if the mesh isn't updated. Secondly, the shader culls triangles that are not in view, and if it bases this on an outdated mesh, some triangles that are visible in the up-to-date detailed elevations may be culled since they are off-screen based on the outdated mesh vertices. We add a small no-cull buffer around the edge of the screen to reduce this effect, but here you can see it happening as the terrain rises significantly without the mesh also rising. Thirdly, the shader's lighting is based on the normals of the mesh. You can see here how the lighting remains constant for a continuous terraforming action and then quickly corrects when the mesh is updated at the end of the action. However, even with these tricks in place, the mesh update would be too slow, causing an annoying stutter if we didn't add one final trick. I'm sure many of you are expecting this one. Breaking the terrain up into chunks is a standard method used to improve performance. It doesn't make sense to update the entire terrain's mesh if only a small part of the terrain changes at a time. I break my largest terrains up into a maximum of 64 chunks, or 8x8. This requires jumping through a few irritating hoops, mainly due to the grid points on the edges between 2 chunks having to be applied to both chunks, and even to 4 chunks when it comes to the corner grid points. But after some head scratching, I figured out a data structure that allows me to do all of this in jobs too. And this allows us to only refresh the so-called dirty meshes where something has indeed changed. Another common issue with chunks is visual seams that appear on the edges between chunks, due to normals not blending properly. This happens because the edge of one chunk doesn't know what the vertex next to it in the other chunk is, causing it to lose that half of the normal calculation. I got around this problem by not using Unity's built-in mesh normals calculator on the chunk meshes, but always calculating the entire terrain's normals with my own method, and allocating the results to the normals of the chunks in the same way as the elevations, jumping through the same hoops to make sure both or all 4 of the chunks are updated at the edges and corner grid points. Luckily, since the meshes are fairly low resolution, calculating the normals for the entire large terrain using burst compiled jobs takes a fraction of a millisecond. There are a myriad other small issues and considerations that are part of this terraforming solution, but let's conclude with one final important one: how to convert the height map stamp into elevation adjustments for the correct grid points. The basic idea is fairly straightforward. You overlay the height map stamp onto the terrain, centered around the mouse pointer. This gives you a square of grid points that may be impacted. Then you adjust the elevation of each grid point in this area with the strength of the height map by sampling the height map at the corresponding point, determined by the relative location of the grid point in the impacted area. However, we also allow the X and Z scale to be set, the stamp to be rotated, and both the intensity and the contrast of the stamp to be adjusted. The intensity and contrast are easy to change since they simply adjust the sampled stamp strength in place. However, the scaling and rotation is more complex. Firstly, the square becomes a rectangle as you alter the scales. Then, as the stamp rotates, or the terrain rotates underneath it, the axis-aligned impacted area expands and contracts to contain the rotated rectangle. All of these changes need to be factored in by adjusting the relative position of each grid point to include the applied scaling and rotation. This has to be done for thousands of grid points every frame as you terraform, so a burst compile job saves the day again. In addition to raising and lowering, we also cater for flattening of the terrain to a pre-selected elevation. Finally, to make it easier and faster to jump between functions, the UI allows many different ways of setting the parameters. Click and hold, click and drag, sliders, or shortcut keys combined with scrolling the mouse wheel. And that's it for this video. Please let me know in the comments which technical areas you would like more detail about, and subscribe to this channel, wishlist and follow Minor Deity on Steam, or join the Discord to stay up to date. All the links are down below. Also, feel free to ask specific questions you may have. Thanks for your time and support.